And thank you for being here on this Friday, last day of the Scuola, of the school on mathematical and computational aspects of machine learning. So we have the Lars Ruthotto opening today. There will be a short break at 10. If you can maybe refrain from assaulting the coffee table. The real coffee break is at 11. Thank you.
All right. Thanks, Michele, and thanks everyone for being back after such a long week. I'll try to make this as very attractive because we have a lot of program, and so we really don't have time for a coffee break in between. Like, I mean, you have me until 11. I want to finish more or less everything that I've prepared, and that will be a tough job. So we have to all work together a little bit, which does not mean you shouldn't interrupt me with questions. So as I mentioned in the previous lectures, I really like questions. That's the most important thing here. Okay, so I left you in suspense for 2 days or so because remember last day, or not last day, Wednesday, what we did, we went to training single layer neural networks, right? So there the idea was that feature engineering that sometimes we can do very effectively by hand and by looking at the data, we now want to outsource it to a neural network. And we started with a single layer neural network, which means you take your data, perform an affine transformation, nonlinearity, and that's the stuff you are going to put into your linear model for classification or for regression. And that, I think, I remember, went quite smoothly. I mean, the training went okay. We had 3 different methods. They all more or less worked. It was a non-convex optimization problem, so some people are amazed that it works, but I also showed you an objective function to show you that it's not that bad in the end. And then we said, okay, I mean, we could go wide now. I mean, if you stay with a single layer, you have one design parameter that is like how wide you make your network or how many rows you put into your matrix that you're going to learn. And in principle, you've seen now universal approximation theorems in like a sketchy version in my talk and in a real version in Philipp's talk. So that in principle should do. Okay, in principle, you can do anything with that. However, it's like there's numerical evidence and some folklore and lots of hype in the news of going deep. And the reason there is, or the idea there is to keep the layers relatively narrow, but use a bunch of them consecutively. And that's been shown to increase performance. And lead to interesting problems. One interesting problem this leads to is if we have a measure of convexity, the measure of convexity really shoots up. Like as soon as you have a bunch of those layers, you run into lots of interesting problems. So here was one plot I showed toward the end, where we wanted to compare a neural network. So that is basically you take your, in this case, just linearly transformed features. And basically have a bunch of layers in consecutive fashion, sorry, I should probably show you that in here. So you take your initial features, you get a y1, and then you put the y1 into the next layer, and so on, until you have reached a final time or final state yn. So that was one model, that was the historic model, and we wanted to compare that with the residual network. So the residual network is the same, but you have this y0 plus in here. And then the y1 plus and so on. That's called a skip connection. And I just wanted to show you that, first of all, with the neural network, you run into non-convexity quite quickly. And I got a few questions about this plot, so I want to elaborate a little bit. So here what I've done is I've created 2 weights, or 2 sets of weights, theta 0 and theta 1. Okay? And from there I can have a linear combination of the 2 of them, which allows me to plot an objective function. So the objective function here means I keep, say, the theta 0 fixed, put the data into the network, and that's giving me, say, my observed data. So it's kind of an inverse crime setting. So I generate my own data for theta 0, and then I look at the relative error between what I'm getting for theta of t, for t moving between, I think, minus 0.1 and 1. So for t equal to 0, you see that you get a 0 here, because you just replicate your data. And for t different from 0, you see a residual. So most importantly, what you see here is that this function is not convex. It's smooth, but not convex. And you also see that in a second. So if I take the gradient of that function and I plot it as a histogram, you see that many of these entries here are relatively small. What small means here is a little bit fishy, but we can compare it now to the ResNet. So for the ResNet, I get a function graph like this. I should say it's not directly comparable. So I use the same weights, but I use a different architecture. Okay, so it's a little bit different. So in the paper that I cite, they do this in a much more sophisticated way, but also they burn a lot of GPU hours to generate a plot like that. Here, that's a relatively straightforward code. And you can see that, say, the relative error here at 1 is actually comparable or even much larger than in the neural network. So I set it up to have a substantial relative error when I change the theta. But you see here that this is basically, I think, a quasi-convex function in this case. There is no theory that should always happen like that, but empirically it's been observed that you see plots like this. And the gradient signal here, sorry for the cropping here, but it's much stronger. So this is here it's like minus 0.2, and here's there you have minus 20. So it's a few orders of magnitude larger gradient, which again. In deep learning, you see these terms vanishing gradient and exploding gradients quite often being used. This would be almost called a vanishing gradient. So your gradient at the point, so this means that the gradient at your current weights is almost 0, but you're not happy where you are. So if you're an optimizer, you want the gradient to be equal to 0, but you also want to find a good solution. And we know that there are many local minima and maybe even saddle points and stuff like that that could all have a so to say vanishing gradient. So that's why we are so interested in working with residual neural networks, because this property has been often cited now. This is just one demonstration of it. Why this leads to much smoother loss landscapes. And so that's the goal of today, to really go into depth now and study the ResNet. So I'll leave the neural network behind and only zoom in on ResNets for the rest of the talk. For that reason and a little for other more theoretical reasons. Okay, and that's a goal for today. So you see there's no time for coffee, but time for question always. Yeah, this example I think I'm going to skip. So that's some ResNet trainings. You have access to the code, so you can run it. These are all codes that you can run within a minute or so on your computer, even though it's MATLAB and it's not a efficient implementation. It's an implementation geared toward understanding. But these ones you can run. It's the same solver as SGD, Newton, BAPRO that you've seen for the other example as well. Yeah, so this probably I gave the summary already. For nonlinear models, we want to overcome the limitations of a linear model by learning a feature transformation or feature extraction. And then you saw the single layer. We talked about the parametric models, so this will come back in a bit also. So where the idea is that you, instead of learning all the weights in this big matrix K and let them all be free, you build a model that you like. For example, a convolution or an M matrix or an antisymmetric matrix, a triplets matrix, a Hankel matrix, whatever you want, or a diagonal matrix. Just to get the number of weights down helps typically with generalization, but even more crucially helps with reducing the flops in your network and your training. And then we went deep. Okay, so and where I really want to go is so the ResNets, since they are a little bit more stable, they can be very deep. Depends how we measure depth. We'll challenge that viewpoint in a bit, but I want to claim for now that we can go infinitely deep. And that's where I want to take you. So, okay, let's go into the section I call continuous models. So here the idea is that we want to understand why ResNets are, I think I call it here more stable, but we want to actually also go much more into depth when they are stable, and sometimes they seem to be unstable. But basically we want to explain why they can be more successful than other networks. And so I made a small change. I don't know if you've noticed on this slide. There is a new player, and that player is called little h. Okay, so people who know PDEs and ODEs a little bit, they missed this already. They were antsy, so we put it here because of popular demand. So once you have put that in, and that was probably one of the main contributions that got us all started when Eldad Haber, one of my collaborators, found this original ResNet paper and scribbled this in and sent it to everyone. So like that was kind of the groundbreaking thing that got us all started, because now you can easily come up with the following idea. You subtract y naught from both sides, you divide by h, and you take a limit. Okay, so then what you see is that the ResNet is a forward Euler discretization of an ODE. So it's an initial value problem here, where your initial value is given by the input features. And then you have a dynamics here that is driven by the neural network. And I made everything here time dependent. So the weights are time dependent, the biases are time dependent, and of course the state is y dependent. Okay? So far so good? So once we have that, the idea that I want to do, the argument I want to make now. Are there questions? I feel there are questions. You can ask me. I'm here. No. Probably, if you have a question, somebody else has the same question too. Happy to explain. Yeah, a question?
Well, I have a question.
Yes.
One of the points that I got from these seminars is that usually you want the feature set, the number of variables at each layer to be, for example, lower and lower, because you want to go from images to a few labels. But if you get to this approach, then in a sense you are forced to keep the same dimensionality.
Yes. I'm going to reveal how that's going to be done in practice. There's a little bit of a gap between theory and practice, but what you have typically in a complete ResNet architecture is you have a finite number of steps where you change the width, but a small number of steps. So not like 2 or 3, say. So here you can think about the y0. Who tells me I have to use the original y0? So if that's, say, in 2 dimensions and I want to have the ResNet in 4 dimensions, one thing very easy to do is I add 2 zeros to it, and then I'm in a higher dimensional space. Or, that's what I do, but what's more commonly done is you replace this by the output of a single layer. And that you can make arbitrarily wide. Okay, so that is a good point that we should keep in mind. So within the ResNet, the resolution can change. But in practice, what's done is you concatenate a few ResNets, and in between you go wider, or you do pooling, or whatever you want to do with the data. So in the original paper, they had 3 of those blocks, and in between, they would downsample. They did imaging, so they would downsample and increase the width and stuff like that. But yeah, within the ResNet, no dimension change. Okay, so the rest of what I'm going to do is a little bit, I have to justify it. So I want to go from this discrete object, which is the ResNet, to this continuous object. I want to study it just for a little bit to gain some intuition and to make some connections to differential equations, to partial differential equations, in order to get ideas how to design a better ResNet. So I'm going to the continuous to get some ideas to do some analysis, but the most important thing for me is to go back to the discrete level, and to go back to the discrete level but with capturing some of the properties that I think I put in the continuous modeling. That is a very delicate thing, so I put in a reference to a very new paper by Uriasha that warns about some of the pitfalls with approaches like that. So sometimes, and we had lots of arguments, and actually we are completely on message on this. You don't want to take the continuous problem too seriously. because the continuous problem is still not really the problem that you're solving in the end. So the main emphasis here will be on the discrete problem, but the continuous problem will give us a lot of intuition. And that is probably similar to what you do in PDE-based image processing or other fields, where you gain intuition on the continuous level, but then in the end, people know you have to solve a discrete problem, and you need to do some work to get the right discretization. So that's just a picture here. If you feel uncomfortable, rightfully so. I mean, you should be cautious, but at least for me, I think I'm fine. Okay, so I want to motivate why so the first thing I want to study is the stability of the ResNet. And why would I want to do this? Because if I think about what it takes to solve a learning problem, I have a bucket list of what I need to do. The main thing is I need to build a model and train it so that it generalizes. Okay, so I need to make decisions. So I need to model the forward dynamic. This is something I want to do in the continuous space. Then I need to discretize it. So the discretization is actually funny. So the discretization of the differential equation will give me what's called an architecture. Okay, so think about doing the ResNet in reverse. You start with the initial value problem. Then you apply forward Euler with a step size of 1, which has always been a good idea. And that is your architecture, your ResNet architecture. Now if you use a different time stepping, in principle you have a new architecture. But it's a systematic way to generate architectures, because you can talk about, okay, which time integrator do I want to use, what kind of step size do I need. It's way less heuristic than you just pull some stuff out of thin air and see what it does. And then you need to train the network by minimizing the regularized loss. And here's my expectation that differs probably a little bit from the other speakers here, and definitely from what some people in machine learning do. I expect that all these three tasks are related. So in other words, if I have the wrong model, even if I discretize it well, the optimization problem will not turn out to be a very nice optimization problem to solve. Okay, the same the other way. So you can play it all different ways. So if you have a really nice forward model, but you use a bad discretization, again the optimization problem is going to suffer. Or if you have a good model, good time discretization, but a bad optimizer, also you're not going to generalize. So all these things go hand in hand, and I think they should be studied together, which is again not so common, because oftentimes you see papers in, for example, optimization journals that just take an architecture and train it twice as fast. And if you do this for a ResNet, I would challenge you to just change the step size and see if your training algorithm still outperforms. Okay. Just as an analogy why stability of the whole model is important, I have a background in inverse problems, and the first thing that we learn when we study inverse problems is that you want to make sure that your forward problem that brings you from the parameters to the data is well posed. Okay, and by that we mean that there is some continuous dependency on the parameters, and also we would want that the inverse is better be bounded. If not, you're in trouble, okay? And so the most straightforward thing is to now look at a ResNet and see under which conditions these two things will be satisfied. Because if an inverse problem doesn't have a well-posed forward problem, what do? You are not a well-posed forward problem. If the forward problem is not well-posed, I think most people will go home, because you wouldn't solve it. It's a meaningless problem. It basically means if you call your forward problem twice, you get different results or so. I mean, it's not going to lead anywhere. Okay, so I wanted, probably I don't need to, but I want to go over at least a little bit about some ODE things. So if we have an ODE, think about here having a time-dependent ODE, an autonomous F here on the right-hand side, but the state, of course, is time-dependent. Then you can study this by looking at Jacobians. You can study the stability, and you want to take a look at the real parts of the eigenvalues. So if they are bigger than 0, it's an unstable system. If they are negative, then it's stable. If it's equal to 0, they are stable, and actually the energy kind of gets preserved more or less. So the Jacobian here really gives you a lot of insight. Once you go to make this like the real thing, so f will be time dependent in our case because the weights are going to change in time, things become a little bit more messy. Okay, so I want to take an easy way out here. I just want to say, okay, I make sure that the weights don't change too dramatically in time by regularization. And that is a regularization that for machine learning people is rather new. For inverse problems people, that's the first thing you do. You basically penalize time derivatives because you have a continuous model. We haven't really studied this then all the way through, but there are heavier tools that you can use to study the stability of nonlinear time-dependent ODEs. But it's really, really tricky. Many things that I believe to be true turn out to be false. For example, you probably know these examples where you have a system where all the eigenvalues are complex at all times. So you think, oh, well, it should be good. But no, you can make an example where the energy still explodes.
But that complex is imaginary.
Yes, it's just imaginary. Yeah, thanks. So there are ways where you can still make energy explode. You need to make the weights oscillate in a systematic way. But anyway, so here only a rough argument based on an autonomous system. So think about all the cases being the same. Okay, so if we look now at a ResNet with this very simple model, we're going to change that. So actually here on the right-hand side, you can write whatever neural network model you want. Okay, so we're going to make that more general later on, which turns out to be important in some applications. So, but if we look at this one, what's the Jacobian? I think I had it on the board the other day. So it's a diagonal matrix consisting of the derivative of the activation and then times the k. Okay. So now, kind of you scratch your head a little bit and you realize it's maybe not so easy to come up with criteria under which this ODE should be stable. So think about, first of all, we make k like fixed in time. Okay, so that's a good step. And we note that for most activation functions, this sigma prime will be greater or equal to 0. That means this diagonal matrix, so you have a matrix K times a diagonal matrix with non-negative entries. Yeah, not so easy to come up with a way to see that this is stable. So for example, you could say, so say these eigenvalues here, the real parts are all non-positive, which would be something you want. But then this diagonal matrix can actually still fool you and make the whole system unstable. So there are all sorts of exceptions here that you have to take into account. So what I think about this then is, in general, when I just train a ResNet, there is no way I can assume it's stable unless I intervene and make it so. It would be a very low probability that your ResNet magically only learns something that is stable. And maybe to give one more reason why you want this is so if you have an unstable system, you probably need much more training data to train it very well. Whereas if you have something that's smooth, the hope is to have something more regular. Okay, so basically we need to enforce the stability. One option is we, for example, can do the following. We can say that J is constant in time or changes slowly. And we can say that we make sure that the eigenvalues are purely imaginary. So under this condition, you would actually have stability. So now the question is, how to do this? I'll show you a few options. But remember we learned the case. So we need to either do regularization or constraints, or what I will do, I will do this by design. So I will design the network so that we have that taken care of. Actually, I realized I did not put a slide on what I mean by stability. It's a terrible mistake. I should probably tell you. So what I mean by stability here is really the low-key version of stability in ODEs. So if you have a y0 here, and you think about the y0 plus epsilon, so if a small perturbation of your input features, I don't want them to do this. I want them to kind of stick more or less together or even diffuse a little bit together. So that is related in machine learning to what's known as adversarial attacks. Because there are instances where an adversary will try to fool your network by adding some systematically adding some random noise or some small perturbation. So if you are unstable, should be very easy to find such a perturbation, and if you are more stable, should be more difficult to fool your network. That's probably the better sales pitch here. But for mathematicians, I mean, the stability, I think, is more. We are more used to thinking about that. Okay, so then I just want to take a little bit of a step back and show you one more way now to look at this deep learning problem. Here's one example, I think, that we've seen before with these peaks data, where you have 5 different classes. And the data is not linearly separable. So the idea now that we have here is that we have this dynamical system that we train to do the transformation that we need to make the data separable. And now I can actually plot this like with trajectories, I mean, I can take a point here and see where it ends up in this frame. And at the end here, so this is the output features. You want them to be so that you can slice them like a birthday cake, like with your classifier. And that's something we've achieved here in this example. How did we achieve this? So there are controls. So here I made it so each little dash is basically one step in my time integrator. So I need to, of course, in the end I need to discretize, and it's one step of my time integrators. And these black frames here, that are controls. So you see, if you sit at least very closely, you see some arrows pointing here. So these arrows depict kind of in which direction should the feature be pushed. These are the ones that you are going to train. Not directly, I mean, not like you don't get to train every single arrow in here, but you are training, say, a single layer that gives you these arrows. So that is one way we can now look at residual network that resembles some problems that we know. One would be path planning problems, where you want to get from A to B. It's similar to optimal transport or dynamic versions of optimal transport. You want to go from A to B at a minimal cost. What is the minimal cost here is a very weird, I mean, we don't have a good definition. You see, for example, here the trajectories are not straight lines and stuff like that. Because we don't encode really the cost of the transportation. We also don't really encode where exactly the points need to end up. We only encode indirectly that they should be in a configuration that we can classify them. So it's not exactly a path planning problem, but at least it resembles a lot of the mathematical structure. So basically now we can study this. Let's say that. We can study this in the like as an optimal control, optimal path planning problem. And the question now actually that I want to put back to you, and we can discuss in the real coffee break. So after we're done with this course, I would be happy to get opinions on what is actually a layer. I mean, what do you want to count? Like the black frames, or do you want to count the dashes? I mean, of course, in ResNet papers, there is a one-to-one correspondence, because at every time step you have different weights. But that's, I mean, that's just a one design choice, and I have many more choices. So I could, in this case, use way fewer parameters than I have in my time integration. And the reason for choosing them, the reasons are very different. So the number of controls or kind of steers how much you can express. Whereas the number of time steps in the ODE is related to stability and accuracy of the time integrator. So they are different animals, really. But if you think about this now, I think one needs to come up with a new way to say what is the depth of a network, and probably we need to report both of these numbers in papers, and also what is the depth. So the depth, I mean, you can think about in continuous, in the continuous time as basically the time interval that you put here. So 0, 1 or 0 to big T or whatever. But it's an artificial time, I want to emphasize. There's no time really in this real problem. So the time loosely corresponds to the hidden layers in your network. But it's not like there's any rule why you shouldn't pick t equal to 2 or 4.5 or something like that. So these are all like interesting, more philosophical questions. So they're not so important for the math now. So that's why I don't want to spend too much time here having a discussion. But you know, if you have thoughts about this, I'm happy to chat more. Okay, so let's look at resonance as a control problem. So if you are familiar with optimal control, and maybe just a quick show of hands, there were a few people I talked to that had experiences in optimal control. Who has? Quite a few, so that's great. So in optimal control, there are basically two big paradigms. Because, I mean, I'm basically optimizing, so I'm optimizing my loss and with a regularizer, and I'm using only the final state of my dynamics that is given by this ODE. So at some point I need to discretize, because I need to go to PyTorch or MATLAB or so. And there are two ways to think about this. One is you can basically first differentiate this whole process, get optimality conditions, and then discretize those. And then there's the option of going the other way around. And I want to contrast them a little bit, because we had some discussions that we had in optimal control in the recent decades have been now really hot in machine learning in the last two years. The real has been reinvented. So I think I should put that here. So if you do this first differentiate, then discretize. So what that means is you keep theta, b, and y continuous in time. You look in your PDE books, there's something called an Euler-Lagrange equation, which is an optimality condition. You get adjoints, and the adjoints, I'm going to show you actually how to derive them. They're similar to that was known as backpropagation in neural networks. Or actually, I would say the backpropagation is just a specific case of an adjoint method. Then you have a system, so you have this system, which is your forward system, and you have an adjoint, which is another ODE that goes backward in time. And you can basically alternatingly solve one and the other. The adjoint gives you a gradient, and you can basically perform an optimization in continuous time. You can also do Newton's methods and so on. What is good about this? You can choose an ODE solver. You can choose two ODE solvers, one for forward and one for the adjoint. And you have a lot of flexibility how to choose them. What is not so good, and I'm going to show you that, is that the gradient you get out of the adjoint method is correct or useful only if you solve both of these problems very well. So if you use a very rough discretization for the forward and a very rough for the backward, I mean, there is no reason to believe that this gradient is going to be related to your forward propagation. I'm going to show you that in a second. And then, but basically, you can do this, and then you can use optimization to obtain a solution, and that is then, of course, in a discrete level. So this approach, I don't know, has anyone heard of neural ODEs? Okay, very good. So that's what the neural ODEs does. And so neural ODEs has been like a paper that actually got a lot of attraction because we received a big award at NeurIPS a few times ago. But it's basically on the idea that we put out on studying resonance in the continuous setting, and then making some of the numerics a little bit sketchy based on this idea. So I'm going to kind of fight back today a little bit. But I want to expose you what is really the problem here in the numerics. Okay, so let's look at how an adjoint equation looks like, if you haven't seen that in a while. So let's think about, we have one example, final time of 1. So we put that into our loss function. And the example is given by our ODE. Okay? So then the question is, how do we get a derivative of the loss with respect to theta? That's what you need to do a step that improves your network. Okay? And in the adjoint method, what you do is you, first of all, so the gradient, so theta is time dependent, so you get a gradient at each time point. And the gradient is given by linearizing the right-hand side with respect to theta, taking its transpose, so that's a Jacobian, basically Jacobian, and multiplying it with z of t. What is z of t? Z is exactly the solution to the adjoint equation. So the adjoint equation has a minus delta t here, because it goes back in time. And here you solve a linearized version of your right-hand side where you take a derivative with respect to y. So that's always a square matrix, because the number of inputs and outputs doesn't change here, as we said. And you have a final time condition. So the final time condition is you take a look at the loss function and just take its gradient with respect to y. Okay? So the way that works is, let's think about a method how to get a gradient. We first solve this equation here, forward time integration. We get a y at time 1, we plug it into the loss function, get the gradient of the loss function as well at the same time, which we use then as a final time condition here. We integrate backward in time, and at each step we can also just get the gradient for the thetas. So you go forward in time, you go backward in time, forward, backward. That's always the notion. And for machine learners, this adjoint solve is really the back propagation. So there also you go through the layers in the forward propagation, you go forward in time, you keep certain things, and then you go backward in time. And it's important to realize what you need to do for the backward propagation, because all these terms here involve the y of t. So there's a y of t in here, and that is also a y of t in here. Which means that you can, in the forward propagation, you have to store the y of t. Or you need to find a way to recompute them. But you need them. I mean, it's not that you can forget all the history here. Okay? Question?
Yes, can you remind me what is C?
C. C is the class label. So it's the loss is trying to match the y to the observation.
So what do you mean? You have one example. Those are vectors?
Yeah, these are just vectors. Yeah, if you have like our usual setting, maybe it's a good reminder for the notation. You have a big capital Y and a capital C, and these were matrices with many columns, and you can derive a backpropagation for that too. But then you need to have some chronicle products here, which it's Friday morning, so we don't want to mess with that. And of course you can do this also by going over every column and sum up all the gradients, and then you'll get that. And in practice, that's what you want to do. I mean, you want to vectorize a little bit these operations. So that's a good point. But the C is really given; it's just a data point. Okay. So the big take home is you need this y of t. No way around it. I mean, and the two options are storing, recomputing, checkpointing. All these things are on the table. But it doesn't go away. And if you train a neural network, I mean, now it's becoming so easy to train these neural networks. There's automatic differentiation. You don't even have to derive an adjoint equation anymore. You may seem that's a skill that is not really useful anymore. But you will realize that your GPU runs out of memory very quickly and very often. And the reason it runs out of memory is because if you do automatic differentiation, it's storing all these y of t's. And even a little bit more probably at any iteration. So that's the reason why it's such a difficult task to train these neural networks sometimes. Okay, so that is you first differentiate, then you and then you discretize in the end your solution. The other paradigm is the one that I for sure prefer for a few reasons, and I'm going to show you some convincing evidence, hopefully. Is you should think about just discretizing this equation. Use whatever method you like. And after you've done that, you have a normal optimization problem, like you find in any textbook. So you have p parameters, you have an objective function, you can take a gradient of whatever you have, and so on. So here you first discretize everything. So the thetas, the b's, the y's, you have a grid for every one of them. I showed you in the picture, you can have different grids for the different quantities if you like. Then you build the objective function, you discretize it, and you take a derivative of that. So for that is what automatic differentiation would do for you. It would give you that basically for free these days. Back in the day, or in our MATLAB code, we had to go through and actually compute them ourselves, which can be done, of course. And so here a pro that I'm going to show you on the next slide is the gradients here. They are always correct. I mean, to numerical precision, you get the gradient of whatever discretization you have put in. Okay? And it doesn't matter if you use only like 3 forward Euler steps, you will still get a reliable gradient. What is sometimes seen as a con argument, but I think actually it's a good thing, is there's no choice of a solver for the adjoint. So the adjoint solver is predetermined by the forward solver. There are some cases where they coincide. So, you know, are like not coincide, where the differentiation gives you a good solver for the adjoint, but not always. So there are a few problems, especially when you have instabilities and shocks and stuff like that, and hyperbolic conservation laws. You want to use a different solver for the adjoint, because you know that you might have some different types of PDEs. But in general, I think it's okay, at least in machine learning, that you just have a predetermined solver for you. Oh yeah.
Y of t is in.
Yeah.
Just to remind the notation, y of t, the intermediate output of a neural network at level t, right?
Yeah, so the t is a fake time, and it roughly corresponds with the hidden features. So you start at t equal to 0, and you go to t equal to capital T. And these ones here, so y at little t, is just a hidden feature, if you can think about it like that. But there is no finite number of layers, it's like a continuum.
Continuum, yes, okay, I got it. And the function f is what, why this constraint?
Yeah, f here is basically your neural network. So that can be now anything that takes a y and a theta, and you know, can be a single layer or other models that we're going to have. So that's just...
okay, so how to interpret this constraint then? So output is the function of neural network. Output of neural network is a function of neural network. Or I don't.
No. Okay, so it's quite easy, because here I wrote it down as a constraint.
Okay.
But of course you can eliminate the constraint. So I give you y0, that's your input feature. So in practice, what you can do to have a code up and running in a short amount of time, you take the y0 and you integrate this ODE that depends on the neural net.
Okay.
Up until time big T. And then you plug that into your linear model and you classify. Okay? So this basically y of big T, think about it just as a matrix that has a number of features and number of examples. But it's kind of the transformed features. So, okay, because there are probably also other people wondering. So here in this case, so this is my y0. So think about this way. Think about this way. So here's my y0, and here's my y of big T. So for each point, you know, it starts at this location, and then you can trace it, and it ends up in here. And now this is the data that I feed into my linear model. And the process how I get there is by solving the ODE. And the controls here, so these are my f of thetas here, basically, those layers. They control what's going on. I mean, we'll have a few more examples later, so then hopefully it'll be a little bit clearer. Okay, so if you do this, so you discretize first, then you differentiate, then you can use any nonlinear optimization method to get a minimizer, and that is what we do in all our papers. And I would also want to highlight this paper, which is written by George Grohs and some of our friends at UT Austin, that basically expose this very nice debate between what should you do first. So this is also known as discretize optimize. There's optimize discretize. It's been a decade-long discussion in optimal control. And now, in order to prevent in machine learning to have all this rediscovery, they put together a very nice paper on exposing some of the pros and the cons here. So I really I can very highly recommend this paper because I'm not involved, but I was very pleased to see it. So here's one thing I tell all my students to do. Sometimes they resist, but in the end there's no way around. If you want to do any optimization, you want to show me that your gradient is working. And here I kind of did that for one of these neural ODE examples that you can find. So in this case, the idea was you find the weights of the neural network so that you have an ODE here, and sorry, I changed to use here for the features. Hope that's not a big deal. Fits a true ODE at some time points. So the way they set up the problem is they set up an ODE. It's not a really serious application. So they set up an ODE, they solve it with a time integrator, grab a few measurements of the ODE, and then they want to kind of train a neural network now to rediscover the ODE. Just say like a test case, okay? But you can think about, in some cases, not having the true ODE and just having a few samples, and then these things could actually be quite interesting. So now the question is, how does the accuracy of the ODE solver, so if you are in optimized discretize, you choose an ODE solver, and the big selling point of neural ODEs is you use a black box. Because then, it's a black box. So machine learning is much more black box driven than numerical analysis, and you alleviate some choices of the user. And if you want to use any ODE solver, I don't know if you've used ODE 4.5 or so, or some other one, you need to pick a tolerance. So then that will be used to do some time stepping and some choices for you. And here I have a picture for you that I should probably quickly write down if you haven't seen those plots. So E0, basically what it does is, so we have here an objective function. So the objective function measures how well do we predict the data at the time points. Okay? And what I show here is basically I take the objective function, let's call it J, at my theta 0, okay? And then I perturb the theta 0, that's my weights, into a random direction. And if I perturb it into a random direction, my objective function is going to change, okay? And I can look at what is the discrepancy, what is the difference between J at theta 0 and J at theta 0 plus, let's say, delta times, let's call this just D, okay? I'm not so creative with letters this morning. So you have this parameter delta, that's a scalar. If we pick delta equal to 0, again we recover the same thing. But if we vary this delta, then we will have more or less of a perturbed version. And so you see this E0 here decaying. So down here, basically, I have the delta. So I start with 10 to the minus 2, and then I go to 10 to the minus 6. And you see this error here goes down. We would expect it to go down linearly in delta. Okay? So it's a log-log plot. So then the other curve here you see is E1. And here I need to probably squeeze a little bit. So again, I have J of theta 0. And now you claim that you solve the adjoint equation and you get a gradient of this function J. That's a claim. So then what I can do is I can basically take this and add delta times the gradient of J that you give me. It depends on theta 0, but I probably don't have the space to add it here. Transpose times my D. So this one here is a first order Taylor approximation of what's going to happen with my loss function. And then I have minus J of theta 0 plus delta D. Okay? So that is my E1. Now so again, this is a guy we want to check. So it's actually a very sensitive test that I've been using for years and years and years, and other people too. I mean, I didn't come up with that stuff. If you only have a very slight error here in your in your gradient computation, you will not see this go down quadratically. So this one you would expect depends quadratically on delta, this one linearly. Okay? And it's a highly sensitive test actually. So in this case, you see the red line here, that is the E1. It's about twice as steep as the blue line. So check, you're in good shape. Okay, you can go on, you can use a gradient descent method or whatever. You're good to go. However, now I picked tolerances here of 10 to the minus 7, 10 to the minus 9. So that's the original ones that I saw in this code. So then, the gradient is reliable. However, the ODE solve here is costly because you have a very low tolerance. You have many time steps, which means many layers, which means, of course, a lot of compute to go forward and a lot of storage because every single time point we need to store something for the backpropagation. So, okay, of course, we want to cut corners. The only way I can cut corners here is I can ramp up the tolerances. Then I have fewer time points. If I do this, though, so if I dramatically increase the tolerance here to 10 to the minus 2, you see, okay, for a while I'm good, but then my gradient suffers. Okay? Why does it suffer? Because the forward and the adjoint, they're both solved to this tolerance, but we know that the adjoint only gives us a gradient in the continuous limit. So you have to make sure you solve the problems well enough to keep that relation. And here is just to and a contrasting method would be to discretize optimize. So I use basically the same number of time steps and just use a fixed number of say Runge-Kutta steps and do backpropagation. And then I would get a graph like that. So I'm going to show you how that works in the training. So here's a training example. So here's this neural ODE with a good tolerance. And here is basically what I can do with an RK4, so Runge-Kutta scheme. I use 30 time steps. They are equidistant. I don't have any adaptive time integration. And we can see how well these things train. So here's the here's the prediction. This is the red line. This is the data that's been given to us. We want to kind of this is a starting guess, so it's a horrible job in fitting the data. But now we're going to iterate a little bit, and I hope this video is the first time I use it. So here you can see that the iterates vary drastically between the methods. And I should say that I'm trying to be really nice here, and I'm using the same frame rate left and right. But if you sit in the front row, I'm printing how much time is spent in each time step. So here's about 0.3 seconds, and here's about 0.08 seconds. And we are done. We fit the data. Here, not so much. And I'm using kind of the same discretization. And I think that's an important point here to make. That is well known again from optimal control. Sorry if I bore you with these details, but it's well known, for example, that the number of time steps on the left can vary by iteration. Typically, rule of thumb is the more complex your dynamics, the more time steps your ODE solver is going to take. So which means actually if you think about training this, of course you are always on edge when you train these machine learning models. You take your GPU, you realize how much memory you have, and you want to make sure you don't run out of memory. You have to plan some overhead here, and if you don't get this right, the thing will crash. So this time actually, maybe I can play it again, and at least I can watch it. So sometimes it shoots up to almost a second per iteration. It goes up and down, whereas here on the right-hand side, I predetermine how many steps I take. So there's machine noise, but nothing else really happens. So that is something, again, that is, oh, thanks. I should play it one more time then, now that we have this nice setup. So that is really one characteristic that we've known for years in optimal control. So we need to make sure that also in machine learning applications this gets much more adapted. It's not so easy. So I told you about this nice paper that the guys from UT Austin have written. I think it should get much more traction, which is why I have it now in all my talks. I think we'll also probably write something about these kinds of experiments because it's something that we should not invest so much time to reinvent it. So it's very well known. And of course, I think I put this here. Guess what? So if I use a worse ODE solver in here, I don't do better. I actually do worse. So numerically, I think there are relatively clear idea how to train these ODE-based models that we should be using. Before this becomes an overall sales pitch for discretize optimize, there's a word of warning too that I should give you. So in discretize optimize, so on the right hand side here basically, the reason, one way to choose your time integrator would be, especially if you're in an ODE setting and you think you have observations, you have a standard deviation typically, or at least you can estimate one for how good is your data. So you pick roughly the number of time steps that gives you that accuracy. You don't need to worry about the gradient, okay? Also, you should think about the stability of the network that you get out. That's very important, actually. So, because if you screw that up in a discretize optimized scheme, it can really lead to trouble. So there, the neural ODEs have an advantage probably. So if you have a cooked up example where you have basically a matrix that is like a differential operator, and I make fake data again with 200 time steps, and then I'm playing a little bit with, okay, how few time steps can I get away with when I evaluate the loss function? So for 200 I would basically get the exact same thing, but I'm kind of try to make it a little bit more interesting by using fewer. So if I use only 5 time steps, I can create objective functions that look like so. Yeah, people are shaking their heads. It's not looking too good from the optimization point of view. And your discretize optimize will probably not perform very well. Again, a neural ODE would figure out, okay, that's not a good time discretization and give you some warning. Whereas when you have enough, you have a nice problem you can solve. Okay, so there is some word of warning in place with discrete optimization. It's also well known. If you have a bad discretization, you are going to pay for it. That's for sure. There's no free lunch. And yeah, the generalization here actually is also not good. So if you evaluate it with different input data, you see much more changes of the minimizer than if you don't. Okay, so with that, I should take a break now, because then the next part will be time discretization and then PDEs. So there's a lot to do. Please stick to 5 minutes. So I see you at, again, there will be more coffee break.
Please take your seat.
More coffee break later. But, and I still have one bargaining chip in my hands, that is the slides, because I was notified that I only gave away 4 slides for today. But I have more than 4 slides. So I'll upload them right after class. It's a little bit more difficult. I need to log into something, and I apologize for not realizing what I uploaded there. But that's sometimes how things work. It's a long file to compile, so I only gave you the 4 most recent slides. Okay, great. So I want to zoom in. So we have talked about stability. We've talked a little bit about optimal control, and that picking a good discretization is a very important decision that we need to make. And that is the next part I want to elaborate on. How do you actually discretize and get an architecture that makes sense? Because we didn't want to stay in the continuous space for too long. So here's the deal. So let's assume that we made our forward propagation stable. Okay, I told you one trick I have. That is that you make it so that the k, for example, only has imaginary eigenvalues. That I think is a legit thing to do. And then we look at the forward Euler method in here, and basically, we take a resonant code, we replace one line to make this stable. My way to make this stable, for example, would be to not have k of t. So basically, we replace this with k of t minus k of t transpose. Okay? I can do that very quickly. It works on GPU. It's a very straightforward thing. So you might think you get away with a one-line change to the ResNet. Okay? But now if I ask you the question, and the front row is of course excluded, is this method going to be stable, like the discrete method? Not always. Or I would say probably never. By which I mean you will not be able to find an H so that this is stable. It's an unconditionally unstable method that we have created. So basically, probably I gave that away already. No, I mean, I don't want to talk about this slide because we need to rush up a little bit. So if I do this and I use the forward Euler method, then we are basically making sure we are on this axis, and you want to be inside this pink ball here that gives you the stability. We all know this picture, I think, from somewhere back in our undergrads. If you want to do this k minus k transpose trick, then you want to do something else. So for example, I mean, now you just flip a few pages in the textbook, and one thing you can find is a scheme like this, which is an Adam-Bashforth scheme, like a third order scheme. You have, of course, there are funny numbers here, but you look them up in the book. And one important structure here is that the update that you do not only depends on YL, but also on YL minus 1 and YL minus 2. Okay, so it's a multi-step method. There is a relation to something in neural network called a dense net. In a dense net, basically you keep the old features and you put them all into your layers. In a dense net, though, you don't see factors like 23 over 12 and minus 16 over 12. Basically, this is all learned on the fly. So of course it's expressive, so you may rediscover an Adam-Bashforth method, but guess what? They have already discovered them. So that is maybe a good way to just use something that, again, you put in some of your knowledge, and you have something that becomes a little bit simpler, because you give a bias to something. And that covers some of the imaginary axis here. That's not the only option. In practice, we oftentimes use Runge-Kutta schemes and stuff like that. And then you are more or less good to go. More or less, so the slides that I skipped, basically the only thing they tell you is that you now still need to think about this H. And you can see this here in the picture, because you want to basically, the H kind of scales where you move up and down on this axis. You want to make the H small enough to have stability. What does small enough mean here? I don't know. No one knows. Because guess what? You're training this theta here. So if a theta is big, stuff moves quicker, you need a smaller h. So there's a kind of a redundancy between the h and the theta. So it's hard to say a priori. We know this from sometimes from optimal control problems or parameter estimation problems for those dynamical systems. That, I mean, it's an unsatisfying answer, but we don't know in practice what you can do. I mean, you can monitor certain things like error estimates and then maybe update your choice. But in practice, especially in these machine learning applications, what we do is we pick an h and then we go, okay? And then never look back. Yeah, question? Is there a microphone?
So you keep the analysis always two cases where you have this f with the activation function as the last step, or so maybe you could think about like having again such a w in front of it?
The W, so again, we will talk about a little bit more realistic choices here in a little bit. There's just one model here to look at. The W, I insist, is a very different thing than the K's. Because the W belongs to our linear model. Okay? Mm-hmm. And the K's and B's are basically the feature extractor, or the things that learn the embedding. And the reason I insist on it, no one else does, by the way, but I do insist on them being different things, is because the optimization problem is going to be convex in the W. And I want to keep this card in my hand that I can use that convexity to, for example, use variable projection and other methods that accelerate the learning. And the W, you have only one W, that is to the very, very end, to the output of all the ResNet.
But then you have the case like the sigmoid, for example, or will you also do you always have a positive function then?
Yeah.
So that's intentional.
That is intentional.
Okay.
Yes, but it's a drawback. Sorry. It was intentional in the very beginning, in our early days, and it works surprisingly often. If you have a 10H, it's no problem. If you have a ReLU, yes, it's a problem because the stuff can only grow. It's a big problem actually. So we will switch to much richer models in a little bit. That will have another K outside. It's not a W, it's a K.
Okay,
but we mean the same thing. Okay, so hang tight for a little bit. But it's a great observation actually. With the ReLU, stuff can only grow. It's not good, not a good architecture. Okay, great. So another option is also to say I split my features. So I have my Y. I can split it into two parts arbitrarily, wherever you want to make a cutoff, and make it a Y and a Z. Okay, nothing really changed. Or I can, add a few rows and call them Z. And then what I can do is I can derive a neural network like so. So where I have first a step in the Z that gets updated based on an affine transformation of Y, but with a minus sign here importantly. And then I update the Y that is updated with something that depends already on the new Z that we got. Okay? Notably, this K is the same K as here, basically transpose. Okay? So that is another way of designing a neural network that you could actually derive from an ODE book. So this method here is a discretization of what is called a Hamiltonian system. So you have a Hamiltonian system in Y and Z. And then the method of choice, or one method of choice, would be something called the Vallée integrator. So it's like a leapfrog method with half time steps. That would, in a Hamiltonian, you know that some energy gets conserved. Which energy here is not so easy to find out because it depends again on the weights and everything changes in time. But at least this numerical scheme here will preserve the same energy. So that is another way to describe or to derive a time integrator. And one really, really nice feature that we've been drawing from a lot is if you write this down, it's a simple observation that you can reverse this. So if I gave you the last Y and the last Z, I can go backward in time and I can compute basically the YL and the YL minus 1/2 from it. Okay? It's rearranging, I think, flipping these equations, make sure there's no typo, but I think we were good here. And you can do this. So why would that be good? First of all, it's an old idea. In PD constraint optimization, especially with hyperbolic PDs, people do that all the time. It's nothing really new. However, in neural networks, we were the first ones doing this, and what we like about it is that not only can I do this on paper, I can also do it numerically, and I can do it numerically stable. So there is something, I put a reference here to something called the RevNet, called the reversible neural network, where the whole idea is that you have Y's and Z's again, and you have black box functions here for the Z and for the Y. Just anything goes, there's no relation between them. And then you can still rederive the equations to go backward in time. I'm not using the specific case of the nonlinearity here to do this. I can do it for any, say, F and G that you give me. But the point I would like to make is not for every choice that you can make is this going to be a stable dynamics backward. Or let's say like this, in general, I have no reason to believe it's going to be stable. So that is actually nice. So this reversibility, one thing you can do, and by the way, I need to make this side note. If you read the original paper on neural ODEs, they basically propose that you can, not store anything, but just get the features back by integrating backward in time. So you just change the ODE from F to minus F, you integrate backward in time. not a good idea numerically. And just to show you why that's not a good idea, so the first thing you should do when you do this is to store the y's, compute back, and compare if you get the same things back. And if you do this, so here's a ResNet that I trained where I followed that advice. I use a good time integrator, so RK4, get a nice classification result, and I integrate backward in time. And here's the error that I'm going to get on a log scale. So I plug in say an x in the neural network. The result goes into the inverse neural network, where inverse here means really I just integrate backward in time, and you see it's not an inverse. It's a big error. If you do this with the discretization that I just showed you, you have an error that is again on log scale, so that's like in the 10 to the minus 14 ballpark, which is nothing. I shouldn't show a picture even. And you can still learn you can still learn the dynamics, and you can still train the classifier. Maybe you sacrifice sometimes a little bit of accuracy in our experience, like 1% or so. But you sacrifice 1% and you have something that actually makes more sense. And oftentimes especially when you have few training data, we typically see benefits of this reversibility. Here, this slide, I'm not going to go through this, just making the point that if you use, so this is a statement you sometimes see, so is any algebraically reversible network reversible in practice? It's a rhetorical question. Of course, no. Here's an example for you. You can study on your own time when I have put up the slides, where I just say, okay, the forward propagation is I'm just using a scalar multiple here and a scalar multiple there. That's allowed in the RevNet, and then I go all the way through, have different equations, and I get some stability conditions that are sometimes met but not always. So be careful when you read these claims. There's still some numerical analysis that you can use that shows you that sometimes paying some attention really makes sense. Okay, so since we have now like 40 minutes left, I can probably go to my favorite topic. So ODEs, so with neural network and ODEs, I mean, I was asked about that in the coffee break. I shouldn't call it a coffee break. In the small break that we had, which did for sure not involve coffee. I was asked about that already. So optimal control and deep networks, there are a bunch of groups working on this. So it's my group, and then I work closely with Elder Tabor in UBC. There is Wainan A, there is George Biros and others, and of course the neural ODE people in Toronto also. So that is getting traction, and I've put so I have a separate document that I don't go through here, which is called literature, and I think I list them all in there. So there are a few papers that come up in this area. So here, this is becoming more mainstream over the last 2 years. I mean, things are moving so quickly that all these papers, like I think Adam Bashforth was already claimed after we put it on the slides. So the beginning joke was always, I mean, open your numerical analysis textbook, see all the time integrators, take them, make a new network, call it something, of course, not related to the original name, and send it to a machine learning conference, and you have a new network architecture, and you draw these new pictures, and everything is good. But this is already being done, so don't bother. I mean, that's done. So now I want to go to PDE-based neural networks. So in PDE-based neural networks, we're kind of the lone wolves so far, but I would like to see more people involved. The distinction now to be made is, so the ResNet, you can always think about it as an ODE. I did not make any assumption on the data structure. If, however, I have a data structure, say I have images, so a special type of data, I can think about what actually happens in the feature space. Is there some continuous analog to that, what I'm doing? And that is the idea here. We will talk about convolutional neural networks and their relation to PDEs, and then make better layers actually that are more expressive. So we'll address that question also head on. So what is a deep CNN? That is a deep neural network with convolution operators in there. So I showed you this trick where you have the K operator, and I had this joker that I can say K is parameterized by a small stencil. Or actually, what we also realized, if you have typically more than one channel in your data, and if you have more than one channel in your data, you actually have a bunch of convolution operators that all talk to each other in there. Okay? So here's one way to write a ResNet with convolutions. This is a little bit in an awkward form here, but that's the form that we have implemented in the code. So first of all, two changes. So I have a KL1 and a KL2 here. And that is addressing exactly the question that I got, that if you have a ReLU here, that stuff can only grow. And that is, to be honest, is more close. It's much closer to the original ResNet paper, where they had this thing, and then another sigma, and then a batch norm, and many other tricks in here. So this is a little bit closer, but not completely there. And then I've introduced this operator PL here. And the idea here is I want to address the change of width in the same, in one equation. So I reserve for myself here the option to choose this PL equal to the identity matrix. That's what we've so far assumed. There was no PL, so we use that. But also every now and then, I want to use basically an operator that has only zeros in there, and then the right sizes. So that's not a square operator. So that way I can model a neural network too. So in a neural network, I would always have an operator with only zeros in there that would just make the sizes match so that my code doesn't crash. So in this formulation here, we can, and that's the way our MATLAB code is set up. We can tackle normal neural networks and ResNets in the same code. It's not efficient. You shouldn't do this when you are on a production level or pressed for time, but it's one way to express that. So that's now the model we are going to discuss. And adding this second part here was for us very crucial when we moved to image classification. In the normal cases, you can typically get away with a 10H, and there's no problem. So what is the node for motivation for this? So now we basically have a double layer in here, and for a double layer you have even more strong approximation theorems. Because for ResNet I don't think there's a dedicated approximation theorem. Whenever I ask approximation theory people, then they say, well, basically, since this is residual and you have 2 layers in there, I mean, 2 layers can learn anything, so it should be fine. But I haven't seen it really written down. I don't have a reference for it, and it's not my main interest here. So the other one is that if you have a ReLU here, then the entries in Y can only grow unless you do something else, like having another convolution. So learning tasks that we want to use PDE-based CNNs for is image classification, image segmentation. That's the two main things that we looked at here. So let's first make the connection between the convolutions and PDE operators, or differential operators in general. So if we have bold y be a 1D grid function, by which I mean I take a function y and I discretize it on a grid, and I use a uniform grid here because that's conventional and that's making my life easy. So I have n x cells with 1 over n or 1 over nx. It should be of a step. Okay. Then if I think about the convolution applied to the grid function, and say I have a stencil with 3 elements, theta 1, theta 2, theta 3, I can rewrite the same convolution, or I can rewrite this stencil here in terms of these 3 guys that I picked more or less randomly, but not completely randomly. So the first one here is 1 to 1 over 4. What's that going to do? That's going to average a little bit. So again, the way to read this, if you're not so familiar, the 2 here gets multiplied. So if you compute the, I call the output z, if you compute zi, so the ith component of it, then you take 2 times yi, and then 1 times yi minus 1 and yi plus 1. Or the other way around. There's always this thing of flipping the kernel. But that's how you go. So, so basically this one here is a kind of an average operator. The second one here, minus 1, 0, plus 1 divided by 2hx, is central first order difference. And then this one here, minus 1, 2, minus 1 over hx squared, that's a second order, this is a discrete second order derivative. Okay, so this I can do, and now I have swapped the weights. Instead of having thetas, I now have betas. But it's really the same thing. I mean, there's a one-to-one relationship between the betas and the thetas. You can write this as a linear system, if you wish. And that linear system for any hx you can pick is going to be non-singular. Okay? So there's a one-to-one relationship between that. And that's also one thing to note, because of course you can write this. I mean, you don't have to use a central difference. You can use a forward difference or a backward difference. It doesn't matter. It all leads to a non-singular matrix in here. Okay? For any x, for any hx, that's important. So because then you can take a limit and you can see. So the first one here, that will converge to an identity operator as the mesh size goes to 0. This one the other ones we already discussed what they converge to. So now if I want, I could basically think about either applying this convolution operator to the grid function, or to any grid function where I pick the hx, discretize, and then apply this operator. Or I could think about the linear combination of those operators being applied to the actual function. Okay? And hopefully there's some consistency. I mean, there is consistency if you update this theta. So the thetas here are going to depend on hx, most importantly. So the probably a better way to parameterize this network would be with the betas, because the betas are independent of the resolution. If you change the resolution here, then this hx and this hx square is going to change. This one is going to keep fixed. So the theta will not really be accurate anymore. Not be consistent, say, with the continuous limit. And that is exactly what we want to do, which is based on old ideas from PDE-based image processing, where you think about where you have a distinction between image data, that's my grid function, and images. That's a continuous function, compactly supported, maybe from some function space, and so on. And so that abstraction we want to use in neural networks as well. Okay. So here is one thing now that you can do and ask yourself. For example, if you train a CNN, who has trained a CNN? Okay, quite a few people. So, and I think Alessandro mentioned that in his talks when he trained a model, that there is something like a resize operation. So typically when you train a CNN, you resize all the images, you interpolate all the images to the same grid size. And that is an important step in the pre-processing. But now you can think about, okay, I train my CNN, which means getting all these thetas. And these thetas, by the previous slide, are resolution dependent. So if I train on one resolution and want to apply the network to a different resolution, am I getting the right thing? That's a question. The next question would be, how do you pick so if you do resize, you give two arguments. You give the image and you give a desired resolution or number of pixels, okay? How do I pick that number? So I want to pick it really small, because then I can learn much quicker. So if I have half the resolution in 2D, I get a payoff of a factor of 4 in terms of speed and memory and all the nice things. Okay? So these ideas in image processing have been used quite a lot. There are image pyramids, multi-level schemes and stuff like that. So here I want to make a connection. So say you have a k little h, which is a fine mesh operator. Say that's given. You've trained it with your neural net. And you ask yourself, okay, so can I come up with a k big H? So that's a convolution operator that works on coarser images. So think about, you train your CNN on a supercomputer, but now you want to deploy it on a smartwatch. So the smartwatch typically has a little bit more constraints. It's a serious question. People are very interested in doing these on-device predictions. But you have, first of all, you have worse camera in your watch. You have less CPU power than a supercomputer. So you want to be really greedy and cut corners here. So if you can get away with finding a k big H that is consistent with the one that you've trained, but does not require you to, say, take a low resolution image, make it a fine resolution image, plug it into the network it was trained on, and go back, then I think you are in good shape. So here's one way to achieve this, and there are many ways. It's an algebraic prolongation. It's algebraic multigrid based idea. So think about the following diagram. So here's your coarse image. You're given this operator, this convolution stencil. So one option to carry out to evaluate the right-hand side is you take the image, you prolongate it, which means you interpolate or you resize. You apply the operator, which gives you this image, and then you restrict, and then you're in here. So okay, now if you want to cut corners, you don't want to go into this bottom half. You want to go from here to here directly. And I want to go there and get the same result. So how do I do this? I need to compute this convolutional stencil here. And the way to do this in this case is by writing down these equations, making some choices. So you can make it a Galerkin based approach where you have the restriction be gamma times the transpose of the prolongation, where the gamma you kind of look up in a multigrid book. And then you can have a unique mapping from here to here. Requires you to solve a 9x9 linear system. Okay? So it's cheap. It doesn't involve any training or SGD or anything like that. It's a closed form solution. This is, of course, the most well-studied problem in multigrid, because you typically have a fine mesh operator, a PD operator, and you want to get a coarse mesh operator. You can also do it the other way around, which doesn't arise in PDEs too much. So I give you a coarse operator and I ask for a fine operator. There you can think about having the 3x3 patch on the fine mesh, the coarse mesh becomes kind of a 5x5 patch or a bigger patch on the fine mesh in terms of pixels, if you want to keep the same area. That, of course, there's no way to make a unique mapping. From like 9 weights to 25 weights, there's some room for negotiation. So you can make it unique if you say you keep the kernel size constant. So if you go from a 3x3 operator on the coarse mesh to a 3x3 on the fine mesh, you'll keep it constant. And that will also happen in a rediscretization. Like we had it on the previous slide with the -101, for example. There's always a three entry operator, no matter what the mesh size is. Okay, so these things you can do to go from coarse to fine. So it's one idea. This is written it out. So what is a prolongation and what is a restriction? You can use different choices. I put one example here where I use these operators. So it's not a Galerkin scheme. It's more based on interpolation and those ideas. Again, I should emphasize that in here, different choices will give you different results because the resolution is so coarse typically. MNIST, you deal with 28 by 28 images. We are not really in the limit, like whatever you do in these prolongation restriction operations doesn't really matter. But in the small resolution, there's a difference that we saw with algebraic and geometric multigrid and so on. But we haven't really gone all the way into these ideas. It's one of the first things we've tried, and for some examples it actually works quite well. There's much more to explore about this idea. And also for some of the things I'm going to assume or I'm going to talk about next. So that is one idea I want to put out. So you should think about the image as a continuous object, and then design operators based on that. That is one line of research that we've started, and where I think there is much more to do. Okay. So the next thing is I've done something here, of course upon request, to add this new operator in here. But now the question is, what does that actually mean for stability? We thought, we had the case closed, stability, one trick we knew, like making it anti-symmetric. Now I think we have to reopen that can of worms again, because we have this new operator. So if you analyze the stability and you look, for example, at the Jacobian again, just as a rough estimate what's going on, you have the K2 here and the K1 there. And they sandwich this diagonal matrix with non-negative weights. And now you can, again, think about, can you come up with eigenvalue estimates or ways to make sure that these eigenvalues are imaginary?
Question.
Yes.
Are you back to the ODE case, or is this like a semi-discrete?
It's so it works actually for ODEs and PDEs, but the stuff I'm going to show you has a very strong connection to PDEs. Sure, you can have this. In this business, anything goes. So. And the K here, yes, is ambiguous if it's a convolution or no convolution. For now, let's assume it's convolution, because there's something really nice I can show you with, and also to motivate a few things. Okay, so this Jacobian here, for me, very difficult to analyze the eigenvalues for general K2 and K1. And I've looked at this for some time, but maybe someone else here has a better idea. It's fine. So one thing I can do to make it stable is I can replace the K2 by minus K1 transpose. Okay, so if I do this, and now I don't have to distinguish between K1 and K2, because again we're back to only one matrix, then this is how my Jacobian looks like, and it's symmetric, negative, definite by design. I made it so. Okay, so in this case. We can see if we have stability. If we wave our hands, we say the K doesn't change too quickly. We have a small enough time step. That is something we call a parabolic convolutional neural network, because with the following choice, maybe I should write that down to show you that motivation. So if you pick K1. Oh, sorry, K. So K is, say, going to be applied to an image Y, and I can make it a block matrix. I can have so if I increase the number of channels in here, then the K transpose will bring me back to the same number of channels. Okay. So one thing I can put in is I can put in a discretization of dx and a discretization of dy. So basically you apply this to y, so then this would be the gradient of y. So if I pick the stencils appropriately, I can model this. That's my claim. And if I pick sigma of x, the stuff I'm not supposed to do, but if I pick it equal to just x, then see what you get here. You have a gradient, and this stuff is basically becoming a divergence. Okay, so that's why we call it a parabolic CNN, because then you can think about this as like a heat equation that you have in time. Okay, what do we know about the heat equation? I was so proud of this movie, so I need to play it. Although you know what happens with the heat equation, you have an input features and they decay. Okay, that is a super stable process. Because if you think about perturbing the initial state, like putting a heat source here in this room, and now over the weekend it's going to be an empty room, coming back Monday morning, find out where the heat source was, no clue. I mean, like everything is gone. So what does it mean for learning? The forward propagation is super stable. Theoretically, again, we have not shown that really in practice. It's much more robust to the perturbation of the inputs. It's hard to actually prove this in practice because it's hard to measure these things in high-dimensional spaces. But the intuition is very strong in that case. The learning problem, so that is the thing, like a forward problem now becomes a heat equation, say. The learning problem, like if you think about the poor classifier who comes back Monday morning and needs to figure out where in this room was the dividing line between presenters and audience, it's not so easy. So the idea is, I mean, don't go to the asymptotic limit. Don't overdo it. Like pick a final time. So as we do in image processing also, when we do image denoising, we never go to the asymptotic limit, which is like a constant image. I mean, don't do it. Okay, but keep that in mind. And of course, numerically, I mean, numerically solving the heat equation is not a glorious task. You can easily do this. So that's a parabolic CNN. There's actually a theorem. That and I are not really known for theorems, but we can actually, prove that even so. Here for the parabolic one, the changes in time, the weights don't even matter. So here we have a very strong theorem that we were able to prove, but not alone. Martin Borger actually gave us the right hint to interpret the operator as a monotone operator, and then it's like a straightforward thing to do. But we needed a pointer to do that. So anyway, so here, for any choice of weights, you're going to be stable if you have a small enough step size. And it's similar to anisotropic diffusion and other very popular methods that we have in image processing. If you pick the right activation function, you can connect it to total variation too. So the tan H actually here gives you a relation to total variation. I think I have a plot for that. The proof I'm going to skip because it's so trivial. I don't want to embarrass myself. So if you think about this, what we've done, you could actually think about the network being the gradient of a potential. So that's an observation. So Stan Osha, when I met him for the first time, the first thing he wrote down for me, was so happy to see something that resembles total variation here. So if you think about a potential phi that is based on a single layer with an activation function S here, the question is, so the sigma is going to be S prime. So we take it basically one step up. I mean, we go to a scalar potential. Typically, we have more than one feature, so we are in a vector field. So if you have a single layer and you have this S here, the sigma typically is S prime. So if you pick the ReLU, then you can see that this would be the S that you have in your potential. And if you pick the tan H, this is what you would get. And if you plot this function, so it's log of xx minus log of x minus x, this is a red line here, then there is some connection to smooth the L1 in this. So this is an absolute value function for the L1. So that way, so if you have exactly this gradient here, and you pick the tan H as an activation function, you can see something that looks similar to like an L1 minimizing flow. So you can do some denoising. Your network could do some denoising if it chooses to want to do denoising today. Because of course there are other operators the network can learn. But there's one nice relation also that now really confirms the claim that this is a stable operation. It's like you can think about the ResNet as a gradient flow on a total variation. So that's some of the nice connections that we have in here. Flip a couple of pages in your PDE book. So that's parabolic CNNs. Okay, you can easily make those. So there are hyperbolic CNNs as well. And this movie, I promise you, is not a cheat. So I'm not taking the movie, play it in this direction, and then play the same movie backward. I actually simulate. You see, the discontinuity is only now. So in a heat equation, in hyperbolic equation, I can do something that I cannot do in a heat equation. I can move stuff backward and forward. I can move my bottle to the left and to the right, and nothing gets lost. Okay. So that might also be a nice structure in a learning problem. For example, the reversibility that I already touched upon. So you can save costs in the adjoints. I mean, the idea is to recompute things. Okay, you pay a price for that, but you don't have to store things, and mostly you are memory bound on the GPU. I don't know how your GPUs are like, but my GPU runs out of memory very quickly, but it can actually do quite a lot of computation. So if you go to hyperbolic regimes, the idea is you can exploit these things in a learning context. I should make an important note. I'm surprised no one has interrupted me for that. So if you train a normal ResNet for those imaging problems, what type of PDE do you think you're going to get? No expectation. Because the network chooses weights, and they can lead to something parabolic. I mean, the network could learn that the outer one is the transpose minus the transpose of the inner one, Okay, could happen. I mean, I don't want to take away that possibility, but the chances are relatively slight, probably. So, and it could even learn like a matrix that is more like a hyperbolic system. I don't want to exclude that option too. And it could learn something that is completely not related to either of these two categories. And think about what you typically do in a ResNet. You train this thing with a you discretize it with a forward Euler method of step size 1. Okay. So my philosophy would be, I pick a PDE that I like, and I pick a numerical method that I know works for that type of PDE. And then I go with it, and I still owe you the proof that this actually works. Because in the end, I mean, I told you can do anything you want, but you need to get results. Otherwise, no one's listening. So that is still a proof I need to give you in the end. Okay, so hyperbolic networks you can design, and we have designed them in two fashions. So one is again based on Hamiltonian systems, where you pick a layer like so. You have and y that gets updated by the z here, with again the symmetric layer that is very important if you want to prove the stability, because you want to bound the eigenvalues of the whole thing. This one here has one has a positive operator, one has a negative operator in the end. And that way nothing gets lost. So you can do that. And we can write it in matrix form, and we have a proof for the Jacobians, the eigenvalues of this. Here, the stability really requires you to have slow changes in time. There's no free lunch here, at least for us. And you could use, I would recommend you use a Velay method, because that method you can discretize the forward and backward. I'm not sure if I have a slide for it, but maybe not. Because you can, of course, now that you think about hyperbolic PDEs, think about, okay, why on earth do I have to stick with a first order time derivative? No one tells you that you need to do that. So what we also have been doing is we just replaced it with a second order time derivative, which gives you something like a wave equation. So you can do that too. That is another way to derive a hyperbolic dynamic. And so that's what we refer to as a second order network in here. So here now comes one of the comments that we had earlier. How does it actually look like in practice when you train these ResNets? You have here is a graph of one recent architecture we've been using. So you would have an opening layer. So there you have a convolution, and you go, say, here from 3 to 16 channels. Go from RGB to something. So that is a single layer neural network. We don't know how stable that's going to be, but it's only one of them. It's not a large number of them. There are some dirty tricks I didn't reveal here. Something is called the batch norm. It's a very awkward object to me. I know other people here have different opinions, but for me it's something I'm uncomfortable with. Because basically the idea is that you couple different examples that just happen to be in a batch together and normalize their statistics. But in principle, every image should be their own example. Here, to make it work, we had to put it in. Okay, we had to kind of defeat our pride. However, within this ResNet block, so these red blocks are really the ones that I talked about, where you can use hyperbolic ones, the parabolic ones, or whatever. There, what we use is something we call the TV norm, which stands for total variation. So there, the idea is you take one image and you normalize only that image, and it then looks very similar to a gradient flow that you have in total variation, because there you have typically the gradient of u divided by, and then gradient of u plus epsilon, norms and squares and square roots and stuff like that. So that's why we call it the TV layer. And that one, from a PDE perspective, it's much nicer because it does not couple different examples. Also from parallel computing, it's nicer, and it actually works. We tried to put it in here as well. Cost us a few percent, would have killed the paper. So okay, we had to publish also at some point. So we're still looking for better ways to replace those operator. And then from left to right, you typically decrease the resolution and you increase the number of channels. That's something we learned from the practitioners in the field. And then you can train it. So here I think I showed some results for the STL10 data set. It's RGB images. They are relatively high resolution for those classification problems. It's like 100 by 100 or something like that. But it's of course nothing close to where we want to be, like in say classifying 3D medical images or so. I think there is no architecture right now that really can do this in a scalable way. And we train it with our favorite method, SGD, some parameters that are typically chosen, and some smoothness in time. And then results you're going to get, and a little bit out of context, probably if you haven't worked on these data sets, is you can get very easily to about 80% accuracy. Before we started this, the best paper that we found was something out of Facebook, which was in the mid 70%. So we have one of our papers that we got into machine learning conferences where we pushed this up by 10% by using these PDE-based architectures. So here we're definitely not losing accuracy. We're actually gaining accuracy. Okay, then you can have funny pictures. I like dogs, so you can see, okay, you have an image of a dog, and you can see, okay, what is here is a blue label. So the blue label is always this light blue. So it's a true label. And then you can see, basically you can plot the prediction of the networks as a vector that is normalized to 1. So you can have a bar plot of this. So in this case, I mean, all the different networks see that's a dog, although I would probably have expected that actually to not work so well because the dog is swimming and has, a stick in his mouth. And then there are also, so I pulled examples where, everyone gets it right. Mostly they agree. But then, one of them fails, two of them fails, and all of them fail. And this one, of course, we can explain what's going on. I mean, generally speaking, you have no reason to believe why your network is doing what it does. But in this one, it's very clear. So they all think it's a bird because the dog is jumping, of course. I mean, that's the only legit excuse. But you can see it maybe. I mean, of course, flying objects are birds. I was surprised it could have been an airplane too, because that would have been an option as well. So that's, I mean, probably one thing about. One thing very important to note here, I mean, with the age of machine learning coming over, and all of us being, I think, more or less excited, otherwise we wouldn't be sitting here on a Friday morning. Explainability is a huge problem. So what we've been doing so far is not really getting us to where we want to be explainable. But at least, we try to do some more math that explains at least the failures. So, for example, stability is a big thing that can explain a lot of failures. But really, the reasoning of a neural network, I have no claim to be touching this for now. Okay. And with that, I probably want to summarize a little bit to have time. Although before the coffee break, no one asks questions anyway, right? So I can just keep talking until the coffee break. So okay, so this lecture was very different from my previous talks. I think here, because which were probably a little bit slow and basic and stuff like that. Today we ramped it up. I guess you noticed to more recent things and more, so to say, also exotic things. But they become a lot of traction, so it's good, I think, to talk about them. So the stability of the neural network takeaway: ResNets are not stable in general. There's no reason to believe that they are. With a few choices, you can make it so. Importantly, actually, there's a sales pitch I recently found out is much more powerful than what I talked about today. So there is a lot of work. I think yesterday in Gabriel's talk, for example, there was an important constraint that the network is Lipschitz 1. The parabolic network is Lipschitz 1. No constraint. I mean, the energy decays. Like, there's no argument. And that's been our philosophy so far, to make sure these things that we want happen by design and not by constraints. Because in an SGD it's hard to have constraints. That's all the burden is done in the modeling before you even start training. So the training goes at the same cost as you would have for a ResNet. So we don't have to train slower. Yeah, and if you do this, the generalization often doesn't suffer. This is a careful argument, because we also see that oftentimes we actually do much better in the learning, especially when we have only a few examples. There are different directions that we look into and that are pretty much open and People are just starting to populate them. One relation is to optimal control. So think about all the things that we know about optimal control. I mean, why not try them out for training these ResNets and improving them? So that's the line of research that we are doing. With some works, I think I have listed them in the literature. Then you can think about the architecture as time discretization. So my recommendation would be, don't worry too much about high order schemes. Because in the end, it's machine learning. I mean, the data is very inaccurate. You're not, sending a rocket to the moon and stuff like that, where that's a big concern. What I'm concerned with is use a stable and symplectic integrator. So I didn't show you this, but there are examples where we've compared, like, say, use an RK4, which is fourth order method, and use a symplectic method, which is the lower order. The lower order one, if you say have a pendulum, we know who won wins. Especially, I mean, of course, not in the limit, but in what you can do on a computer with big time steps. So that's much more important to me, and oftentimes low accuracy is only needed. So don't stay in the continuous space for too long. If you do PD-based, you have a space-time continuous model. So multi-level schemes could be good ideas. You can become resolution independent, both in the training and also in the analysis of these objects. Hopefully that gives more insights, similar to what has been achieved in PD-based image processing, where similar abstractions have been made. Then you can make a ResNet parabolic or hyperbolic even in two different ways. And my idea would be you commit on a PDE type that you like and that you think is adequate. And then you use a stable discretization for that. I mean, surprisingly, didn't dwell on it too much in the result. So in the classification accuracies, the parabolic network does does as well as the hyperbolic networks. So it's kind of really something we need to gain more understanding of, in which situations the one is superior than the other. I also was asked about that. I didn't have slides for this. Of course, all the time integrators I presented to you are explicit schemes. Of course, the good question that I was asked is, okay, well, why don't we do implicit? Implicit because we are not brave enough to do it. It's requiring nonlinear solves in each step of the forward propagation and then back propagation through that thing. So maybe not for me. We've done some work on semi-implicit methods where we add and subtract a linear term. It's similar to what happens in what people have done in PD-based image processing. And then we treat one of them implicitly to gain the stability that we want and also achieve more coupling. And for that, we use the trick I revealed yesterday where we think about a convolution as being computed with FFTs, because then you can compute and invert it at the same cost. So there are definitely some more things coming up there. Maybe as a mini course summary, again, I mean, I hope I didn't promise too much, that we took a look under the hood. Because we read this scary quote that no one knows what these machine learning things do. Hopefully we get at least one line of attack now, and maybe have a starting point now. We have the linear models. Again, they are your foundations. We need them. With nonlinear models, and as you get deeper, actually it's harder to optimize. I mean, I swept it under the rug. But training these ResNets, no matter if they are normal ResNets, parabolic, hyperbolic, that is still a headache. I mean, it's not going in an afternoon. And we have only scratched the surface. So you find nice challenges also in recurrent networks where it's really a nice ODE interpretation, generative models, autoencoders, reinforcement learning. That's for tomorrow. And with that, I'm sorry to have spoiled that in the beginning, but that's a picture. We can. I just want to thank the organizers again and the participants, because I really enjoyed all the discussions we had here and had a fantastic week. So thanks a lot.
I'm going to do a breach of etiquette, and instead of asking if there's any questions, I'll ask the first question.
Okay. I thought we would just declare defeat and say before a coffee break there are no questions anyway.
No. So what about SDEs instead of PDEs?
Oh yeah, so Stan Osha and his group, they have one paper where they use the Feynman-Katz formalism to make the resonance more stable. So I have some actually really interesting results. I have that paper listed in my literature review. So the idea is to inject noise smart noise, you need to do a little bit of analysis there, into the resonant forward propagation. So you do a forward propagation, you add some noise, and that is known to lead to more smooth dynamics. Yes, okay. Good option.
All right,
great question, actually.
Here we come.
But too late, unfortunately, Michele. It's been done.
So first of all, thanks again for this wonderful course. So one general question regarding the entire course is that somehow it seems to me that we focused on so matrices, so kernels, etc. But for activation functions, we basically stick to just a few most well-known and most well-used. So is this some kind of general message that you're also giving, that, or is there space? I think that there should be space also to work in that direction on more general activation functions.
I mean, thanks for this question. I mean, that's a good one. No claim that these are the best activation functions, and no claim that it's not worth looking into better ones. You have to realize, and maybe I conveyed that, if you really want to train, to model, train, and put everything together in these networks, this is very labor intense. So, you know, we cut corners where we could. So if we found, okay, these are the activation functions everyone's using, we just use them. We don't have any original idea in this so far. I know that, for example, if you look into variational neural networks that are very much related actually to the parabolic network, Tom Pock actually has some nice ideas about how to also train the activation function at the same time. I mean, you would lose the theory a little bit because they would not necessarily be monotonic. But again, I mean,
I guess that I'm asking because we are actually working with Tom Pock.
Yeah. Yeah, no, that makes a lot of sense to try it. And again, I mean, you can do whatever you want, and as long as you get results. So. And we didn't explore all the options. There's no claim for that.
Other questions or comments?
I was wondering regarding the explicit solvers. So do we get from this evidence that there's a relationship between the resolution and the step of the ODE? As in a CFL.
Yes, so of course that would be the big the expectation. In fact, so if you train on a single resolution, you don't realize that that could be an option. But sure, if you go from coarse to fine, typically I'd expect that you would want to update your step size and make smaller steps. And it also makes sense. There's a problem in machine learning called the field of view problem. Which means if you think about it very, very naively, if you have a convolution stencil with a 3x3 kernel, in each application of this, the region of influence, if you think about a delta function being in 1 pixel, grows only very, very slowly. So that is one relation too. If you have more high resolution images, you need much more steps to transmit signals from one corner of the image to the other one. So there, I think what we have been proposing was the semi-implicit scheme, because there you have an inverse convolution operator, and that has a bigger influence area of influence there. But certainly, you need, in principle, for higher resolution, you need more time steps, which makes everything like much more expensive, because not only are the individual operators more costly, you also need more of them. Or you need other ideas, like semi-implicit or fully implicit schemes.
Thanks.
Okay, I suggest we go for coffee, and if there's other questions, you can ask directly the speaker, whom I would like to thank again for this course.
Sure. 10:03.